Hello, welcome to Basics of Finite Element Analysis. Today is the third lecture for the current week, and yesterday we had discussed weak formulation, and we will continue that discussion today as well. So, in the last class we had developed a weak formulation for a particular differential equation, and that weak formulation was 0 equals 0 to L dw over dx ax cj So, this is the weak formulation. Okay. Now, I wanted to make couple of very important points in context of this weak formulation. First is that, as we have several times earlier discussed, that the requirement because of this weak formulation for differentiability on the dependent variable u, it gets reduced. If it is a fourth order differential equation, if we do it 2 times, I need only a function which is differentiable 2 times. If it is second order, then I need only a linear function which will meet the requirements. So, that is one thing. The second thing is that this, and this is also we had discussed in the last class, was that this boundary term which comes out through the process of integration by parts, it actually helps us satisfy the natural boundary conditions identically. So, in the strong form we would have to choose these shape functions in such a way that they meet natural as well as essential boundary conditions. If I use the weak form, then I have more flexibility in choosing the shape function, and the only thing I have to worry about is that the shape function should satisfy the essential boundary condition. The third thing is, it also helps us classify what kind of boundary conditions are involved. So, we will discuss this in detail. So, let us look at this. So, you have in the boundary condition, there is this thing which is the shape function, which is in green, and then there is something in red. Okay. So, there are 2 parts. So, the boundary condition it involves weight function and that is in green, and then it involves dependent variable in red. Actually, at this stage I will replace this by u du over dx, okay, which is mathematically the same. Okay. So, it is dependent on it's a function of the dependent variable function. It is not dependent variable itself, but it is a function of dependent variable. So, this is like the coefficient of weight function. There is w, and we can treat ax du over dx as the coefficient of weight function. Coefficient of weight function now in second order equation there is weight function. In a fourth order equation we will have to integrate it two times. So, first we will get a weight function and second time when we integrate we will get a derivative of the weight function. Okay. So, if there are weight functions in the boundary terms or there are derivatives of the weight function, then their coefficients, coefficient of weight function and its derivatives okay, they are known as secondary variables. SV, secondary variables. And if I, so in this case it is Ax du over dx, okay, that is my secondary variable. And if I specify this, then I say that I have specified the natural boundary condition. Okay. So, this is a logical way to say which one is natural boundary condition and which one is the essential boundary condition. So, this is one. The second thing is if we express the dependent variable in same form as weight function and its derivatives, then it is called as primary variable. And if I specify it, I say that I have specified the essential boundary condition. Okay. So, to make things clear, in this boundary term, the weight function appears as W. In the boundary term, weight function appears as W. If I express the dependent variable in this equation, the dependent variable is U. We had discussed, mentioned this right in the beginning. So, if I replace W by U in this boundary term, then U is my primary variable, and if I specify it, I say that I have specified the essential boundary condition. In case of a beam, so this is the equation for a bar, right? This equation represents a bar or rope in tension or electrostatic problem and all that. But suppose there was a beam, it will be a fourth order differential equation, and there when we integrate it two times, we will get these things. There will be a weight function and there will be its coefficient. This is what we will get in the first integration, and when we integrate it second time, we will get this, and so this will be the first boundary term. And this will be the boundary term after second integration. Okay. So, in this case, and this happens because the governing equation for a beam, Euler-Bernoulli beam, is a fourth order differential equation, right. So, in this case, my second primary variables will be, there is W, so corresponding to that there will be U, and there is W prime, so corresponding to that will be U prime, where U is the deflection of the beam. Okay. U is the deflection of the beam, and the secondary variables will be EI. So, excuse me, this should have been not W, it should have been U, because U is the unknown we are trying to solve. So, it is E I u prime prime and the whole prime. This is what? It is the shear force. It is the shear force in a beam. This is the formula for the shear force, right? And E I u prime prime, this is my shear force, and this is E I u prime prime is moment, bending moment. Okay. So, my essential boundary conditions are u and u prime, my natural boundary conditions are shear force and bending moment. So, if I have a beam, I have to specify two conditions at both the boundaries. At either I specify, so total number of boundary conditions I have to specify are 4 and 2 on each end. So, either I specify u and boundary bending moment or u prime, or so combination of these two. So, at a pinned end my displacement is 0, right, and corresponding to the second thing my bending moment is 0, and at the fixed end, at the rigidly fixed end cantilever, my u prime, which is deflection, is 0 and the slope is 0. Okay. So, all these boundary condition terms, they naturally come out when we do the weak formulation, and you can classify them and separate them, and then by looking at the physics of the problem you can figure out which conditions are known and which are unknown. Okay. So, you can have situations where all the essential boundary conditions are known. For instance, you can have a beam like this. In this case, u prime and u are known at both the ends. So, all EBCs are known. Or you can have another situation so it is a beam, but I am bending it by applying a moment at both the ends. So, in this case bending moment is known at both ends, and because I am not applying any vertical shear force, so shear force is also known. So, in this case at both ends I know the natural boundary conditions, and in the third case, which may be something like this, I may have a mixture of some essential boundary conditions are known and some natural boundary conditions are known. Okay. So, this is the way we can specify and classify different boundary conditions, and the next point in context of weak formulation we are going to discuss is that how do we make the choice of weight functions, because till so far what we have been saying is that if there are n unknowns corresponding to n Cj's, right, C1, C2, C3, then we will choose n different weight functions, and because of that we will get n different equations and we will solve those to find the values of C's. So, now we will discuss that, at least in context of weak formulation, how do we go around choosing appropriate weight functions. So, choice of weight functions. Okay. So, in general we choose W such that it vanishes at the boundary if the primary variable is known at the boundary. Okay. What does that mean? Suppose I have a bar and I am pulling it and I am also applying some traction on this. X at x is equal to 0, u is equal to 0, right. Then when I am making a choice for weight function, I have to ensure that W is 0 at x is equal to 0. Okay. What could be an example of such a weight function? One example could be x, another example could be x square, another example could be sin pi x, and so on and so forth. Okay. So, this is one. Another case, so here I am applying a force. In this case, this is the same case, but here instead of applying a force, I am displacing it, let us say by 5 millimeters. So, u at L is equal to 0.005. In this case, what is our primary variable? Primary variable is u, right? We have discussed what is a primary variable and secondary variable. So, primary variable is u, and u is known as at x is equal to 0 and x is equal to L. So, if u is known at both x is equal to 0 and x is equal to L, then I have to choose w which vanishes at x is equal to at both ends. Okay. It has to be 0 at both ends. W should be such that it is 0 at both ends. It could be any function, but it has to meet because because u is known, even though u is non-zero at x is equal to L, my choice of w has to be such that it should be 0. In the first case, u was not known. I was applying a force, but I do not know how much the bar is going to stretch. Here I am actually pulling it by 5 millimeters. So, x is known, u is known at x is equal to L, and also u is known at x is equal to 0. So, in this case, we will look at few boundary conditions. So, it could be 1 sin pi x over L, another could be sin 2 pi x over L, sin 3 pi x over L. This could be one set of functions, right. Another function could be x times x minus L, another function could be x times x minus L square, and so on and so forth. So, this is how we choose the functions. Now, these functions will not work. So, let us say this is case A and this is case B. So, these functions will not work for case A. Why? Because if we choose these functions, then we have overly excessively restricted our choice of functions. Okay. Here the only restriction is at x is equal to 0, u is 0. So, I cannot have the weight function behave in such a way that the weight function becomes 0 at the other end of the rod. Okay. So, the next thing is that why do we make such choices? Why do we make such choices? Okay. So, the first reason is that we have to choose these weight functions in such a way that they represent variations in the primary variable. They represent variations in the primary variations. So, choose, so in a general sense, choose W such that W is a variation of U. Okay. It is a variation of U. And if you remember our discussion of variations, the variation of U, suppose you have a string and it is suppose u is 0 at this end and u is 0 at this end, then the variation of u could be any function as long as no, not small, because the smallness is dictated by that amplitude alpha, if you remember, as long as it does not violate the end conditions, right. Wherever the variable is known, at that place variation has to be 0. At all other places it can be non-zero. So, if I choose these functions for case A, I will not truly represent the variation in u, because I will be specifying that variation at the other end of the rod is also 0. So, once again I will like to restate that we choose w in such a way that they represent variations in the dependent variable. Wherever the dependent variable is known, at those places the value of w has to be 0. Wherever it is not known, the w need not be 0, w need not be 0. These variational, so w represents variations, or I'll tell you, and in mechanics it is also known as virtual displacement. And maybe in the next lecture we will see why we are doing all this, why we are doing all this. So, if I do this, then my governing equation, so my original governing equation was this weak form this is the original weak form of the for the system, right, and my boundary condition was u at 0 is equal to some constant u naught and a du over dx at x is equal to L is 0. Okay. So, what I can do is I get the same term here minus w a u prime x is equal to L and plus w a u prime x is equal to 0. Okay. So, what I have done is I have just expanded this term in the parenthesis. Now, I know that du dx at x equals L is 0. I am now going to enforce this boundary condition. So, this term becomes 0. Okay. So, this whole term goes away, right, or I can, yeah. So, anyway, so this is what I am left with, this is the thing. Now, if I replace w by variation, then I get this is the equation I get, where w is represented by a variation in w. This form where I am replacing w by variations is known as variational form. it's variational form. And a lot of times this weak form and variational forms are, lot of times they are interchangeably used, they are used interchangeably. Other point, that if the differential equation is linear and of even order, then we will see that weak form is symmetric and bilinear in U and W. So, if you look at our original equation, this equation is linear in U, we do not have a U square term, right. And what is the order of this differential equation? This is a second order differential equation, right. I have U prime and then it is going to get differentiated one more time. So, it is a second order differential equation. So, it is of even order and also it is a linear equation. And for such equations, when we construct a weak form, this is another form, weak form, or this is another, this is weak form, then you see that you have this term W prime AX U prime, or you have this thing. So, this term is, we had discussed this earlier, it is symmetric. If I replace W by U and U by W, I get the same thing, right. So, this weak form is symmetric and bilinear, okay. It is symmetric and bilinear. The third thing is, so we have said that differential equation is linear and of even order, weak form is symmetric and bilinear. And the next point to make is that because W represents variation in U, it represents variation in U, its nature should be similar as that of U. It should belong to the same space as U, it should belong to the same space as U, okay. And what that means is that when we are choosing different options for picking up W's, we do not have to see when we have made some choices for picking up J's, right, which represent U's. We can use same functions to represent W's also. So, that makes our life easier, So, this concludes our discussion on this particular topic, at least in context of weak formulation. Now, in the next class, what we will discuss is three other concepts: linear, bilinear and quadratic functionals. And then we will show that when we are multiplying the error with a weight function and we are integrating it over the domain, and then when we are creating a weak form of this, we are actually minimizing some overall function. And in context of solid mechanics, essentially what we are doing is that we are minimizing the total potential energy of the system, which, and whenever in solid mechanics we minimize some total potential energy, that is the state, that is the condition for its equilibrium. So, that is what we will discuss in the next class. Thank you.